So today's warm-up is actually a little different in that it's not a new. This is a recycled. So this is from an old exam. In fact, this was from the exam from last fall, if I recall. So what was it? Well, here you have plotted surfaces, and we have pictures. Over here, we have formulas. And these formulas produce pictures. Among these pictures, the formulas exist. And the question is, okay, pair them up. Now, if you count, you'll see that there's 8 pictures here, but there's only 5 formulas, which means that we threw in some extra pictures for fun. Or maybe you could say for misdirection. So let's see if we can figure some things out. We don't necessarily have to go in order. Some things sort of stick out a little bit nicer than other things. As an example, look at the second one. X squared minus y squared equals 4. What do you notice about that formula? X squared minus y squared equals 4. There's no z, which means what? Well, it means you should get the same thing if you move up and down along the z-axis. So if you see anything that varies as you move up and down along z, then you can roll it out. So for instance, this changes, and that changes, and that changes, and that. In fact, almost everything changes as you move up and down along z, except one thing. And therefore, we can see that this is the only part where there's sort of a missing variable. We called this a cylinder last time, but you can just say, look, you know, if there's a missing variable, it just means that you're photocopying up and down. That's if the z is missing. You could have the x be missing, in which case you're photocopying left and right. All right, so that one's not so bad. Okay, so let's see if there's another one that's not so bad. Well, let's take the first one. X equals y squared plus z squared. Now that's not exactly like one of the formulas we talked about, but it's kind of close. So what was it kind of close to? It looked a lot like the z equals x squared plus y squared, where essentially you had one variable is equal to the sum of the squares of the other twos. Now if you have z equals x squared plus y squared, what was that shape? It was a parabola. It was a bowl shape. So what happens if we move the variables around? The answer is it's still a bowl shape, but now we just sort of change our orientation. So you could say that x is the new z. All right, so I'm looking for a bowl shape that's opening up along the x-axis. All right. Now, you'll notice that we have 2 bowl shapes, C and F. The rest of them aren't. Okay, so we've narrowed it down. Which one opens up along the x-axis? Is it C or is it F? It's C. Now, you might say you haven't explicitly labeled, but if you were to zoom in really, really close, there's this little tiny dot here that under a microscope says Z. So this is opening up along the x-axis. In general, the convention is X, Y, Z. Okay, so this opens up along the wrong axis, so this is C. All right. Let's move around again. Let's look at this one. You have essentially, if you don't worry about the 9 and the 25, x squared and y squared and z squared. When you see those combined, x squared and plus y squared plus z squared, what do you think? You think sphere. What do the 9 and the 25 do? Well, they essentially are just sort of stretching or squashing the sphere, and so you get an ellipsoid, or essentially the 3-dimensional form of an ellipse. Kind of looks like an M&M. Is there any M&M type shape that we have? Yeah. A. Hopefully someone was saying A, and they weren't like, from one of our neighbors from up north. A? Oh, what's that, A? No. All right, A. All right, good. So we're now down to the last set. Okay. So z squared minus y squared plus x squared equals 1. Do we remember what that looks like? Or what kind of thing it is? Well, Maybe it's not the most obvious, but okay. This was a hyperboloid. And it's actually a hyperboloid. Well, I don't want to give it away. We'll talk about which kind of hyperboloid it is. Now, one thing you could do is you could say, well, if I'm not exactly sure what it is, suppose for a second, let's see, what can we do that's most convenient? Well, here's sort of like what I would do. I would say that this can be rewritten as x squared plus z squared equals 1 plus y squared. So x squared plus z squared, that looks like a circle in the xz plane. And what's happening is, as I vary y, the circle will either shrink or expand. So that, when I get y equals 0, so y equals 0 would be along here, I should see a circle of radius 1 in the xz plane. So at y equals 0, x squared plus z squared equals 1, which means my cross-section should be a circle of radius 1. All right, so let's think about it. Now we can eliminate anything we've already circled. Now at y equals 0, what that means is I'm taking a cross-section in that part right there. So I'm in the xz plane. Do I see a circle if I take a cross-section here in B? No. What if I take a cross-section over here in D? Do I see a circle? No, I don't see anything at all. I completely miss. What about over here in E? I don't see a circle. I see a parabola-like shape. All right, F, still a parabola. Now, by process of elimination, see, this is like those SAT exams. Just eliminate things, and that's good enough. The only place where we see a circle would be here in H. That's looking very circlacious, which is not a word. But you made me think it's a word because I said it. All right. But you can also see that as I move along in the z direction, I'm getting circles that get bigger and bigger. So the further I move away from y equals 0, the bigger the circle gets. And that's what this is saying. As you move a lot away from y equals 0, this side becomes a larger number, which translates into a bigger circle. So that means that this answer is H. All right, so now, only one more to go. So y squared minus x squared, y squared minus x squared minus z squared equals 1. Now for that one, I would probably start by saying, let me rewrite this. This says that x squared plus z squared is equal to y squared minus 1. And again, I can think about, okay, I'm moving in the xz plane, and as I vary y, I'll get things that look very circle-like. What happens when we put y equals 0? What do you see? X squared plus z squared equals negative 1, which translates into what shape? Translates into nothing. Nothing satisfies that. Well, which one, when we sliced at y equals 0, gave us nothing? D. D gave us nothing, so the answer has to be D. So this is a way to sort of attack these problems. If you're not sure, just start saying, okay, let me think about slices. What happens in slices? What type of shapes do I have? You know, can I recognize it if I rearrange things? Do I have a missing variable? So forth and so on. All right. So that was our fun review problem. So now we're on to a new topic, and today we're going to do something a little bit different in our calculus class. We're actually going to do calculus. All right, exciting times. So where do we start? Well, we're going to start by talking about what we call parametric curves. Now, if you remember, in Calc 2, we talked about parametric curves. So the idea of a parametric curve is we have a particle that we can think of as traveling through three-dimensional space. So I have this particle moving around, and at any given time, I can think of where the particle is at. So oftentimes we think of this t. This is what we call our parameter. So the word parametric is from the idea of there's this parameter. So at any given time, I can figure out where I'm at. So I can say, to figure out my location, I say, what's my x-coordinate, what's my y-coordinate, and what's my z-coordinate. And once I have those coordinates, I have my location. All right. Now, I was able to go and the math department, we're not quite as well off as engineering, so we can't afford all the fancy 3D stuff. But we did have a little bit of budget left, so I was able to purchase my advanced 3D sort of thing to give this idea of a parametric curve. And it's, you can have all sorts of interesting things. So like here's a parametric curve. But see, now my 3D technology, I can rotate it. Wow. See, yeah. This was like the budget for last year, so I hope you appreciate that. All right. So at any rate, I can describe things in 3D. So again, as I vary t, I think of particle as moving along. All right. So the particle moves along. Now, what do we have? Well, the problem right now, it's not a bad problem, but the problem we have right now is we don't have a really good tool to work with points. Because when you think about calculus, at the end of the day, calculus is based off essentially addition and scaling. That's what it's based off of. And then a lot of algebra that goes along with that. You can't add points, you can't scale points. But what can we add and what can we scale? We can add and scale vectors. So we're going to do something, which is to say, instead of thinking about this as a parametric curve where I think about it as points, I'm going to imagine that I nail down one end of a vector at the origin. Then I have this vector that points out to my current location. And I say, okay, so where is the end of that vector? Well, it's at the point x of t, y t, z t. So I can replace my parametric curve with the following, namely a vector where the entries of the vector are themselves functions of t. So I get x of t, y of t, and z of t. So our very fancy thing was essentially we turned our end things from parentheses to these little angled brackets. And at first glance, it seems like we haven't done much. But see, now with that ability to add and scale, now it's like, woohoo, we can do calculus. All right, good times. Now, if we're going to do calculus, where do we need to start? We have to start with limits. Oh, there was a great, people are excited, right. Limits, they're our favorite subject. Now, remember, what are the limits? The philosophy behind limits are they say, what should happen? In particular, as we are getting closer to something, what should be happening? Now, the technical definition, which I will preface this by saying you don't need to know the technical definition, but here's a technical definition. We say that the limit, as t approaches some number, c, of f of t is equal to L, if for each epsilon greater than 0, there's a delta greater than 0, so that the distance between f of t and L is less than epsilon if the difference between t and c is less than delta, but t is not c. See, we don't want t to equal c, because we don't want to say what's happening at the point. We want to say what's happening near the point. This sounds very confusing, but after 5 or 6 years of thinking about it, it's a little less confusing. So, but really, whenever you see absolute value, that's just a way of saying close. So I want the output to be close if the input is close. That's what limits are saying. The output is close if the inputs are close. That's it. And once you understand that, you can save yourself a couple years of thinking about it. Now, what happens with vector-valued functions? Well, the answer is it does the same thing. See, we have this function called capital F of t. So what do I mean here? So this right here, we'll call it here capital F of t. It's a function where our input is time, our output is a vector. And what do we want? Well, we want to say the limit approaches a particular vector if the difference between our current vector and the vector we want to claim as the limit is small, as long as our input is close to our desired value. So our output is close if our input is close. In other words, it's the same philosophy. We haven't changed anything. But once you understand that, then something really beautiful happens. And so the question is, how do I know if two vectors are close? So intuitively, what do you think? How can I tell if two vectors are close? Or what should be true about the two vectors? In particular, what should be true about the components, those entries in the vector? They should be close together. And that's the big aha type moment. So, if you want two things to be close, they should be close entry by entry. And so, what does that mean? Well, you want to look at limits entry-wise. What happens to each entry? And that's going to be a big theme of what we talk about today, is look at it entry-wise. When we're doing our calculus, we're going to do it coordinate by coordinate. So, let's do a limit problem. Find the limit as t goes to 0 of the vector value function t squared minus 1, e to the t, and sine of t over t. Now what we do is we say, okay, instead of thinking this as the limit of a vector valued function, we say, look, we need to have each entry. So we're going to pass the limit into the inside. So limit as t goes to 0 of t squared minus 1, limit as t goes to 0 of e to the t, and the limit as t goes to 0 of sine of t over t. All right, and now we just work on each entry. Well, what happens as t goes to 0 of t squared minus 1? Goes to negative 1. We can plug it in. What happens as t goes to 0 of e to the t? Goes to 1. We can plug it in. What happens as t goes to 0 of sine t over t? Well, goes to 0 over 0, which normally means more work. But sine t over t isn't just any limit. It's one of our favorite limits that we learned from Calc 1. And this goes to 1. And that's the answer. So we can take limits entry by entry. So that's good. Well, what about derivatives? How do we do that? All right. Well, the answer should not surprise you. So here we go. If I want to take a derivative of a vector valued function. So when I have a vector valued function, I have my vector valued function. I'm doing 3 dimensions. These arguments work in any number of dimensions that you want. So I have my f of t, g of t, h of t. And well, what do I look at? Well, I look at the limit as some thing goes to 0. In this case, I'm going to use b. So f of t plus b minus f of t over b. That's just the definition of the limit. Now, notice what I said before. It's all about adding and scaling. Look at what's happening in the limit of the derivative. In the top, we are subtracting, which is just adding under a different name. And then we divide by b, but that means we're scaling by 1 over b. So when I talk about adding and scaling, that's what I'm talking about. Derivatives boil down to that one idea. You add, you scale, and you have a limit. And we know we can add and scale vectors, and we can take limits, so therefore we can take derivatives. So what do? Well, we rewrite the top. It's a vector valued function. So we write, we use our addition fact, we use our scaling fact, and we say, okay, it's really the limit as your parameter b goes to 0 of this expression here. Well, now, what did we just learn? We can take the limit of each entry. Which means that if you can take the limit of each entry, what you get out is you get the derivative of each entry. So if I want to take the derivative of a vector valued function, I go through and I say, let me take the derivative of the first one, the first entry. Let me take the derivative of the second entry, and so forth and so on. However many entries there are. Could be 2, could be 3. You could go into some advanced class and have more than 3. I don't know why, but okay, that's fine. So let's do an example. All right, find f prime of t given that f of t is some vector valued function. So now we need a vector valued function. All right, what will the first entry be? So give me a function.
X squared plus 2.
Okay. X squared plus 2 is not a bad idea, but notice our parameter is t, so we'll change it to t squared plus 2. Very good. All right, thank you. We go to our second entry. What? Cosine of t. All right, good. You're hopeful that I'm going to be nice to you if you're nice to me. We'll see if that pays off. The last entry.
Sine squared of t.
Sine squared of t. All right. Perfectly great function. Perfectly great function. All right. So, what's f prime of t? Well, f prime of t, you go through it entry by entry. The derivative of t squared plus 2? 2t. Derivative of cosine of t? Negative sine of t. And the last, the derivative of sine squared of t. So we think of it as sine squared of t. Think of it as the function sine being squared. We use the chain rule. The 2 comes down. Sine of t to the first power times the derivative of sine, which is cosine. All right, good. Now, you'll probably notice, like, hey, that's not so bad. It's a lot like what we had before. Because it is like what you had before. But see, now, we can just sort of like have 3 times as much fun. Because it's not asking you to take one derivative, it's asking you to take a derivative 3 times. See, that's why it's multivariable. You get to do multiple amounts of work. So, all right. Good. Well, now one of the things we want to figure out are saying, let's do rules for derivatives, because derivatives can be tricky if you do everything by limits. So it's nice to have some rules for derivatives. Now, derivatives work entry-wise. So the rules are pretty simple. So, for example, if I have 2 vector valued functions being added, I want to take the derivatives. I just take the derivatives of each one individually and I add them up. Similarly, if I scale, I can just scale the derivative. So this is a way of saying here that derivatives are linear. They work in a nice way. All right. Well, another rule is the chain rule. So here, what do you have? So you have to be a little bit careful, because when we think about the chain rule, it's not that you put a vector valued function into a vector valued function, because that usually doesn't make sense. But what you can do is you can take a function, we usually call them scalar functions, but that's just a fancy way of saying, you put a number in, you get a number out. So g of t is one of those functions where you put a number in, you get a number out. Capital F is a vector valued function. This is a type of composition, in other words, function inside of a function, that makes sense. We can still work with it. So if I have capital F of g of t, what happens? Well, take the derivative of the outside, so it's the vector valued function, f prime, of g of t, and then you multiply it by g prime of t. Now, how does it work? Well, it works entry-wise. And these rules are pretty easy to check entry by entry. All right, what's the other type of rule that we usually like to talk about? Product rule. Now, let's think about vectors. How many different products do we have with vectors? There are 3. Do you remember them? Scalar product, dot product, cross product. Now, you have to be careful because they're all defined. They do different things. So you have to think about what the rules would say for each one of them. Now, some of them work pretty straightforwardly. So, for example, if I take the scalar product, that means I want number times vector. So here, this little f of t, that's a function where the output is a number, and then g, that's a vector. So in that case, it turns out that it works like what you expect. Take the derivative of f prime of t times the vector valued function g of t plus f of t times the derivative of the vector valued function g prime of t. All right, because that's, scalar products are fairly nice. Now, dot products, it turns out that dot products are also nice. So if I take a a vector valued function, dotted vector valued function, then what I do is I just say, okay, let me take the derivative of each one in turn. So I take the derivative of the first one, capital F prime, and I dot it with the second one, G, capital G. And then I add capital F dot the derivative of the second one, G prime. All right, well, those two were pretty good. The rules for making them are not too crazy. And then we get to the cross product. And there, it's also nice. Because math should be beautiful, right? So it does what you think it should do. And all this can be verified working through things entry by entry. When you get to things like the cross product, there's a lot of chasing notation, but there's nothing surprising here. So the moral of the story is that the rules are going to generalize like you expect that they should. So things should be nice. Things should work out in a very nice way. All right. So we can talk about our derivatives now. Well, now that we have a derivative, our next goal is to talk about our tangent lines. Okay. So, I have my space here, and I have some vector valued function doing something unusual, but that's okay. There's my vector valued function. And I can ask the question, what's happening at a particular point? So if you think back to our philosophy, remember what we said. Well, imagine that you took this point and you were to zoom in. And if you zoomed in, it would start to look flatter. And if you kept zooming in, eventually it would look very, very flat. So when we talk about a tangent line, we're talking about that zooming in, you're going to see something which is flat. And what is that? So there's some line which touches along this parametric curve and just touches at just the right spot. All right. So let's think about it. Well, if I want to have a line, what information do we need? Okay, I think someone said slope. What do we, instead of slope, when we go up to multi-dimensions, what do we use? Direction, which is a vector. Okay, we need a vector. What else do you need? A point. Now the good news is we have the point. Namely, the point where we touch. So that's our point. But that's not enough. Oh, you can't even see that. It says the word point. I promise it does. Because I'll rewrite it. Point. There you go. Now, how do we figure out direction? Okay. Need point and direction. Well, here's what we can do. We can say, you know, the way you figure out a direction is let's think about a vector. A vector says I just need to look at 2 points. So what I'll do is I'm just going to imagine I'm zoomed in, and I'm just going to pick a point close by. Say that point right there. And what I'll do is I'm going to look at that vector. Well, of course, the problem is that vector is going to go to 0, but we can fix that by scaling it by an appropriate amount. So what I really want to do is I really want to compare where my point is, say, capital F of t, versus where it is if I just perturb it ever so slightly. I want to compare these two. I want to get a vector between them. So in particular, I want to look at capital F of t plus h minus capital F of t. So that's this little vector here. But again, because the vector is getting small, I'll divide by h just to make sure I get something of the appropriate size. Okay, well, what does that look like? It's a derivative. So that's the beautiful thing, is it turns out that your function, so if I have r of t is x of t, y of t, z of t, that gives the location, that gives the point. The derivative gives the direction vector. Because the derivative is talking about your change. How are you changing? And so that tells you in which way you should move. And in particular, you can think about the derivative is telling you what is that particle doing at that moment. Where is it moving? So there's like one of Newton's laws, that says, particle in motion tends to stay in motion unless it's acted on. So what that derivative is telling you is like, okay, suppose you just sort of stopped and let the particle move freely, it would move in a straight line. That derivative is telling you the direction of that line. And it also gives you some sense of how fast it's moving. All right, so let's do an example. Find the tangent line to the parametric curve, and we actually don't have it here, so we're going to make another one up, at time t equals 0. Okay, so we need another curve. So the first entry, what do you want?
Natural log x.
Okay, so first off, we need t. So natural log. And I'm going to avoid natural log of t. I'm going to put in a t plus 1. Just because natural log of 0 can be tough. Very tough. It's one of those zooming off kind of things. Okay, what else?
Arctan of t.
T cubed and arctan of t. Someone knows how to pander to the instructor. All right, good. All right, these are all wonderful choices. All right, so we want the tangent line. Well, what do we need? We need the point. And so for the point, we take r of 0. All right, well, that's natural log of 1, comma, 1 cubed, comma, arctangent of 0. But we can simplify these numbers. Natural log of 1, 0. 1 cubed, 1. Arctangent of 0? Oh, it is 0 cubed. I am sorry. We have such a boring thing here. Let's change it to t cubed plus 1. Okay, 0 cubed plus 1 is 1. Ha ha, ha ha ha, ha ha. All right, thank you. What comes next? Take the derivative, r prime of t. Derivative of log of t plus 1. 1 over t plus 1. Derivative of t cubed plus 1. 3t squared. Derivative of arctangent of t. Oh, come on, come on. Okay, thank you. 1 over 1 plus t squared. All right. I was worried about you. This generation, what's happened if you don't know the derivative of arctangent? All right. Plug in 0. You'll get 1, 3, 1. So now, this is our direction. And you might say, wait a second, Steve, you said that's the point, but that's a vector. But remember, the way that it's set up is that the vector valued function is we can relate vectors to points by saying, oh, it points to the location where you're at if you start at the origin.
1, 0.
And so it would be at the point 0, 1, 0 here, right? So, all right, let's add a 3t here. So then we get 0, then we get plus 3, and now it's 3. Okay, there we go. Problem solved. All right. You can do whatever you want on the test. You may not get credit, but we appreciate the creative answers. And I'll tell you, I've learned more about arithmetic and algebra than I ever wanted to by reading student solutions on exams. So, all sorts of interesting facts. Who knew? Who knew? Okay. Well, let's finish up, and hopefully I won't screw the last part up. All right. So, point 0, 1, 0, and then the vector plus 1 times t plus 3 times t plus 1 times t. Okay, so there we go. There's our line. There's our line. All right. Okay, I should escape before I make more errors here. All right. So the next one, we're going to sort of continue on here. For the same parametric curve as in the previous example, so we will, I guess we should write that down for reference. R of t equals, it ended up being log of t plus 1, comma, t cubed plus 3t plus 1, comma, arctangent of t. And the line, again, we'll write that down for reference. X equals t, y equals 1 plus 3t, and z equals t. Okay, so for that same parametric curve as in the previous example, find the plane which is perpendicular to the parametric curve at time t equals 0. All right. So I want to find a perpendicular plane. So what's the picture you should have in your mind of what's going on here? Well, you have your three-dimensional space, and then you have a curve that's moving through your three-dimensional space, so it's doing something. And now at a particular time, what we're trying to accomplish is we're trying to chop that curve. It's like we're slicing it, but we're not just slicing it in any way. So what we're doing here is, because you can imagine you can slice in different ways. We want to slice so we're exactly perpendicular to the curve. So how do we figure out the plane? Well, if I want a plane, what information do we need? A point and a normal vector. Okay, so since we're after a plane, and of course the reason we know we're after a plane is it tells us. So what we need is we need a point plus normal vector. Now, what can we do? Well, for the point, I need to slice the curve, so it's going to be the point on the curve. And we established that that point was 0, 1, 0. What about the normal vector? What do you need? We need derivative. So why? What's happening? What is that normal vector coming from? I mean, certainly the derivative is the right way to go, but can we think about why? What's the geometry happening?
The tangent line is parallel to the point at that point. So the plane would have to be perpendicular at that point.
So there's this discussion here. Okay, so if I want to understand what the function is doing, one of the best things to do is just imagine I zoom in. So I think about, okay, I'm slicing it with the plane, I zoom in. So the picture would be, all right, if you zoom in on this point, so pull out your various zoom in technology, you're still going to see a plane, but what's going to happen to your curve is it's not going to be looking very curvy anymore. It's going to look more or less like a line. That's what's going to happen when you zoom in. That's what you're going to see. And that line should be perpendicular. Now the question is, which line does that? Well, the line that you see when you zoom in is the tangent line. And so as we zoom in, we see, okay, so the tangent line is that flat thing. So I can replace my function locally by a line. And so I say, all right, so I just need that direction of that line. That's my perpendicular direction. All right, so what is our direction going to be? Do we know it? Or do we have to rederive it? It is 1, 3, 1. We got that from taking a look. It's the direction vector of the tangent line. So here, when we're looking at the plane that slices the curve, it's going to be the same as the normal vector comes from our derivative. Well, once you have point and normal vector, then you can write down your equation for the plane. So remember, for a plane, if you have a, b, c as your normal vector, you're going to get ax plus by plus cz equals some number d. So for us, we're going to get x plus 3y plus z equal to something. All right, how do you find out the something? Plug in the point. 0 plus 3 plus 0 gives us 3. And that's it. All right. So tangent lines, perpendicular planes, we can find them. We use the information about the function and about the derivative. All right. Now, suppose we have r of t is a vector which has constant magnitude. We want to argue that the vector value function r and its derivative are perpendicular. So that's our goal. If we have something which has constant magnitude, then its derivative is perpendicular to location. So, interesting. Now, let's think about how we could figure this out. First off, how do we know if two things are perpendicular? Dot product is 0. All right, so we know our goal, because we know almost nothing about r of t. So we want to be very generic. So we want to use a tool which is very generic. So we want to think about a dot product tool. Okay. There's this other fact. R of t has constant magnitude. Okay. So that means that if I take the magnitude of r of t, it's equal to some value. Let's say c. C for constant. So let's think about what we have. We are given the fact that the magnitude of r of t is equal to a constant c, and we'd like to somehow get dot products involved. So we start rummaging around in our tool chest and say, was there any fact that connects magnitude and dot product? Yeah, so there's this cool fact. If I were to square both sides, I would get that r of t dot r of t is the magnitude of r of t squared, and that's equal to a constant squared. Now here's another fun fact. If two things are equal, what's true about their derivatives? They're equal. So let's take the derivative of both sides. Let's start with the derivative of c squared. What's the derivative of c squared? What? It's 0. Because we're taking the derivative with respect to t. T is what's varying. We're thinking of c as a constant. Okay, so 0, that has to equal the derivative of r of t dot r of t. Well, this looks like some sort of a product rule. Do we have a product rule for dot product? Yes, we do. So the derivative rule for dot product says, take the derivative of the first, leave the second alone, it's still a dot product, plus the first, dot, the derivative of the second, r dot prime of t. Now, let's remember rules for dot products. What happens if I switch the order for dot product? Nothing, it stays the same. And then, so what I see is that these two terms are actually the same thing. So I can put them together. So that's 2 times r prime of t dot r of t. And therefore, because we can divide out by 2, we can say that r prime of t dot r of t is equal to 0. Well, that means they're perpendicular. All right, so there you go. Now you might wonder, well, what's interesting about this fact and why do we mention it? We will actually use this in the near future, but let me just point something else out. You could imagine that you might be living on some sort of a round object. So there are actually people who believe that the Earth is round. We call them round earthers. So anyways, round earthers, they claim that we live on a sphere. All right, well, that's, okay, everyone needs a hobby. But what you can imagine is if you live on a sphere, see, a sphere is really cool. It has the following property in that if you're on a sphere, you're always equidistant to the center. So what you can do, sorry, my picture got a little bit crowded there, is if you're on a sphere, you can imagine that you actually travel along the surface of your sphere. So when you're traveling on the surface of your sphere, if you think of what's happening, if you put your center at the center of the sphere, what's true about the magnitude of r of t? It's constant. So as you move along the sphere, your derivative is always perpendicular to your motion. All right, well, let's just try this out. So here's a claim. So there's a parametric curve, and it's given by the following. R of t is 1 minus sine of 2t, and then that's the first entry. Root 2 times cosine t plus sine 2t, and then cosine 2t is the last entry. The claim is that this has constant magnitude, and we want to verify that r of t and r prime of t are perpendicular. And this is what the curve looks like. It's a little bit hard to see from the perspective, but it's sort of moving up and down, moving around. It's somewhat... someone came up to me yesterday and said, you know, what do you call the saddle? Couldn't we call it a Pringle? And probably you could, but, you know, they started using, they came up with math terminology before we had corporate sponsorship, so we know. Maybe nowadays we would call it the Pringle. But, okay, so it's sort of Pringle-esque, if you will. And in particular, to show it has constant magnitude, says there's actually this sort of like, there's this sphere sitting here in three-dimensional space, and this curve is sort of moving on the outside of that sphere. All right, so how do you show something has constant magnitude? Well, the answer is you take the magnitude, and you show that it doesn't depend on t. So, for simplicity, I'll just square it. If the magnitude is constant, the square of the magnitude is constant. And then I can save myself writing square root symbols. So I want to look at 1 minus sine of 2t squared plus root 2 times cosine t plus sine t squared plus cosine of 2t squared. Now, if you work this out, and I'm going to go a little bit fast here because we're almost out of time, what you'll get is you'll get from the first term 1 minus 2 sine of 2t plus sine squared of 2t. From the second term, the square root of 2 squared, so you get plus 2 times cosine squared t plus 2 cosine t sine t, and then plus sine squared t. And from the last term, you get cosine squared of 2t. And now you start playing your matching game. Sine squared 2t plus cosine squared 2t, what does that give you? 1. I should have also pointed out, what does 1 give you? 1. Cosine squared plus sine squared? 1. And then there's a 2 times there, so that's plus 2 more. And now we have this sort of part there, and then like part over here. But hold on, 2 cosine t sine t, what's that equal to? Double angle sine 2t. Then there's a 2. So that's 2 sine of 2t minus 2 sine of 2t, cancellation. And therefore, the magnitude is constant. There's no t. If there's no t, that means it doesn't vary as you change time. So, and then if you take r prime of t and dot it, you will see you get 0. I'll leave that as an exercise. We already know it's going to be 0 because the theory says so. All right, that's it, done.